Okay, so here we're going to run through homework 3, exercise 15, which a few different students had requested on the homework request form. I'm seeing 3 different requests for it, and we're just going to run through it. So here's the premise. We have this sphere, which I'm going to draw like this. And the key idea is that 90% of its surface is red. So it's mostly red. And 10% of its surface is blue. So there's a little bit of blue, but it's mostly red. And what are we trying to do? We're trying to prove that regardless of how we color it red and blue, we can put a cube into the sphere such that all of the vertices are on the sphere. So maybe let's make our cube green for a minute. And we're drawing it in such a way that all the corners of this thing are touching this sphere on the inside. Okay. And right now, how I have it drawn, let's just say that these vertices here are red. This one and this one. And again, the way that I have it drawn, this one is blue and this one is blue. Okay, so right now, 6 out of the 8 vertices are red. Okay, we want to show that we can rotate this cube around somehow, such that all of the vertices are going to be red. All right, so first things first, we're going to try and figure out the expected number of red vertices. We'll start by labeling them, R1, R2, all the way up to RK. Maybe we think of each of these vertices as having a number. It's not really too important which one. 4, 5, 6, 7, and 8. Okay. And RK is going to be the event that vertex K is in a red part of the sphere. So right now, RK is occurring. And the indicator variables say that our indicator variable 1 sub r sub k is going to be 1 if r1 is going to be 1 if rk occurs and 0 if it doesn't. So, for example, here we have that 1 r1 equals 1 because it's red. 1 r2 equals 0 because our second vertex is blue. 1 R3 equals 1 because our third vertex is red, and so on. Okay, so for an event A, how does the expected value relate to the probability? Well, what are we going to have? We're going to have 1, so our expected value for some generic event, A, is going to be 1 if A occurs, which happens, well, probability of A, plus 0 if A does not occur. Okay. And then we can just cross that out. That's 0. And so how does the expected value compare? The expected value of an indicator is just the probability of the event. Okay, next we want to write the number of red vertices. And we have this really handy way of doing it. Look, it's 1 if it's red and 0 if it's not. So if we just add up all of these indicator variables, we're going to get 1 plus 0 plus 1 plus 1 plus 1 plus 0 plus 1 plus 1. Of course, you'd probably do it in a more systematic order. And so here's our answer for A, and our answer for B is going to be the number of red vertices is R1 red plus is R2 red plus is R8 red, all of the way up. That's our function. Okay, and now what's C asking for? C is saying, okay, though that function is also a random variable. Let's just copy that in there. Maybe let's make it a little smaller. This is also just a random variable. So we're allowed to compute the expected value of that. That makes sense. And what we're going to do is we're going to use this hint, linearity of expectation, which just like derivatives says that, like if we were going to take the derivative of an expression like this, we'd just do it one part at a time because derivatives are linear. Similarly, expected value is linear. So this is going to be equal to the expected value of the indicator of R1 plus all of the way up to the expected value of that indicator variable on R8. Okay, well, now we can find its expected value by doing a couple of little tricks. So the first little trick is going to be, what did we say? The expected value of the indicator is just the probability of the event. So this is going to be the probability of R1, the probability of R8. We add them all up. All right, and then let's just think about one of them. So I think this is the trickiest part because you go like, wait, these events are definitely not independent. And that's true, they're not independent events. They're definitely not independent events. But that's okay because we can compute their expected values sort of one at a time, and that allows us to just add up their probabilities. So what's the probability that a given vertex is in a red part? Well, it's sort of equally likely to be anywhere, and 90% of the surface is red. And so this is going to be equal to 0.9 plus 0.9, and there's 8 of these. And so this is going to be 7.2. Okay? And this maybe feels weird. Again, these events are not independent, but we use this linearity of expectation trick to compute the thing. So we sort of got to treat them almost like they are, even though they're not. Okay, and then lastly, what's D asking? D says, why does this answer imply that we can position the cube in such a way that all of the vertices, are all simultaneously on red parts of the sphere? Well, if we're sort of averaging these things up, if our average is greater than 7, which it is, that means that not, maybe I'll say it this way, that means that at least some orientations of the sphere, really orientations of the cube, have more than 7 red vertices. In other words, if we're just averaging up things that are less than or equal to 7, well, then we're never going to get something like 7.2, right? So that's the idea of how you do homework 3, exercise 15.